Let's now see some examples where we use pumping lemma to show that a given language is not context-free. Let's start with the following example. Let's say the language L is defined as follows: 0 to the n, 1 to the n, 2 to the n, such that n is greater than or equal to 1. Note that if we didn't have this 2 to the n part, just 0 to the n, 1 to the n, we have already seen this language in our previous lectures, and we have seen that although this language is not regular, we can show that this language is context-free. Basically, we can design a PDA that recognizes this language. Informally, in the PDA, when we go over processing the symbols of the input string, we can push all the zeros that we see into the stack, okay, and at each time non-deterministically guess that we have reached the middle of the string, and in the second part we can now start popping the zeros that we had pushed earlier corresponding to every symbol 1 that we see in our input string. And at the end, once we finish the processing of the input string, if the stack becomes empty, then this implies that the number of zeros that we had pushed earlier in the first part of the string is definitely equal to the number of ones in the second part of the string. So we can design a PDA for such a language if we don't have the part relevant to the 2's. But now if we have this language which says n zeros followed by n ones followed by n 2's. So this language consists of all such strings. Now you should be able to see that if now we are required to check the number of 2's as well, then things get a bit hard for a supposedly existing PDA for such a language. Because let's try to do something similar as we had done assuming 2's didn't exist. We would normally push all the zeros into our stack, and then in the second part we would now pop all the zeros that we had pushed earlier corresponding to every symbol one that we see in the input string. But then once we finish processing the ones, the stack will be empty, and we will have no way of checking whether we have exactly n 2's at the end of the string, because now we have lost the information that we had stored earlier into our stack. Okay, so it seems like this type of a language seems to require at least two types of indefinite counting, because we want to be able to count zeros versus ones and also ones versus 2's. Okay? Therefore, we guess that this language is not context-free. To formally prove that the language is not context-free, we will use our pumping lemma for context-free languages. Let's start by picking a special string S. Our string S, in this case, we pick it the following: 0 to the P, 1 to the P, 2 to the P. Let's see if it's okay to pick this string S. There are two conditions to check whether this string is okay or not. One is that the string must belong to the language, while the string consists of P0s followed by P1s followed by two P2s, which is okay with respect to the definition of the language, so string is inside the language. The second condition is that the length of the string should be greater than or equal to P. And the length of our string is 3p, therefore this condition is also satisfied. So it's okay to work with this string for the rest of the proof based on pumping lemma. Let's try to visualize how the string S looks like. According to our pumping lemma, we should be able to partition S into 5, U, V, X, Y, Z. And how does the string itself looks like? We have a bunch of zeros followed by a bunch of ones followed by a bunch of 2's. Number of zeros at the beginning is P, followed by P many ones, followed by P many 2's. Now for the rest of our proof, we will try to investigate all the possible cases based on this middle substring vxy. Case 1, the first case, and if at each case we can show that there is I such that uv to the I, xy to the I, z is not in the language, then we will be done with our proof. Let's say for case 1, we consider the following scenario. vxy, the middle substring, contains only one type of a symbol. One type of a symbol. How does this happen? We have our zeros followed by ones followed by twos. This is our string S. Now, since vxy contains only one type of a symbol, vxy might be among the zeros here, might be among the ones, or might be among the twos. Let's give them subcase numbers. Let's say this corresponds to subcase 1.1. vxy is somewhere among the initial zeros. Let's call this case 1.2. vxy is somewhere among the ones. And this case 1.3, vxy is somewhere among the twos at the end. vxy is here, or vxy is here. Okay, let's first consider the subcase 1.1. We will see that the other subcases 1.2 and 1.3 are similar. For case 1.1, let's try to visualize how a new substring uv square x y square z looks like. So uv square x y square z looks like the following. We will have a bunch of zeros followed by a bunch of ones followed by a bunch of twos. Note that in this new string uv square x y square z, since we are assuming vxy belongs to the zeros at the beginning, in the new string there will be no change among the substring that contains ones and twos, because we are assuming in this case that this modified part of the string vxy belongs to the initial zeros. Therefore, number of ones in here will be the same as the original string, which is p. Number of twos did not change either. Number of twos will be p. Now we know that we assume that vxy belongs to here, and by condition 2 of our pumping lemma, we assume that length of v and y together is greater than 0. This means that one of these substrings v or y is non-epsilon, okay, which implies that in this part of the substring v square x y square z, we must be increasing the number of zeros in the new string. So the number of zeros in the new string must be greater than the number of zeros in the old string, because v or y is not epsilon. V or y contains some number of zeros, and if we repeat v y in the new string once more, this means that number of zeros in here is now greater than p. Now, since this is the case, we have more than p zeros at the beginning, followed by exactly p ones, followed by exactly p twos, then it should be clear that this new string uv square x y square z does not belong to our language L, because the definition of our language is that we have strings of the following format: 0 to the n, 1 to the n, 2 to the n. The number of zeros, ones, and twos are equal. However, in this new string that we have generated by pumping v and y twice, we see that the new string contains more zeros than ones or twos. Now, the other cases, this case where 1.2 where vxy belongs to ones, or 1.3 where vxy lies among the twos, are also similar to this subcase 1.1, so I won't go into detail in those subcases. So 1.2 and 1.3 are similar. This handles the first case, case 1, where the middle substring in here, vxy, contains only one type of a symbol, either zeros, ones, or twos. However, this is not the only case. We can have other cases as well. Case 2. It could be the case that this middle substring vxy contains two types of symbols. Vxy contains two types of symbols. So let's again try to visualize the string S. We have P many zeros followed by P many ones followed by P many twos. For this scenario where vxy contains two types of symbols, it could be the case that vxy is somewhere here that contains zeros and ones, or vxy contains ones and twos. Let's call this first case as a subcase. Let's give it a number, 2.1. Let's give a number for this one as well, 2.2. Let's again only investigate one of them because you should be able to see that the other case will also be very similar. Let's first concentrate on the subcase 2.1 vxy, where vxy contains zeros and ones. Let's now consider, so for 2.1, let's again concentrate on uv square x y square z and assume that this is the case. So if we consider uv square x y square z, note that there will be no change to the number of twos, because we are assuming vxy belongs to this range that contains zeros and ones. So in the new modified string uv square xy square z, in uv square xy square z, there are p twos, symbol twos, because in this new substring the only modification happens only on this part. This part is not touched. Therefore, the number of twos doesn't change, and it is the same as in the original, which is p. And now we can use the second condition of our pumping lemma, which says that length of vy together is greater than 0, or in other words, v or y must be non-epsilon, which implies that if v is non-epsilon, then v contains zeros, or maybe it contains zeros and ones. Whereas on the other hand, if y is non-epsilon, y contains ones, or y contains ones and zeros. Okay? But in any case, in either case, if v or y is non-epsilon, in this new string uv square xy square z, since we are repeating v and y twice, it should be clear that in this new string the number of zeros or the number of ones must increase as compared to the original string s. So in the same string in uv square xy square z, it must definitely be the case that greater than p zeros or greater than p ones must exist, because we know that v or y is not epsilon. Okay, now combining these two observations together, there are p2s, but it's the case that number of ones or number of zeros is greater than p, then uv square x y square z does not belong to our language L, because according to the definition of our language L, we have to have the same number of zeros followed by the same number of ones followed by the same number of twos, whereas these two together is contradicting this definition. Therefore, the new string is not inside the language, and this actually completes our proof, because we can use the same argument for the subcase 2.2 as well. This will finish our discussion related to case 2, where vxy contains two types of symbols, and you should be able to see that case 3, where vxy contains three types of symbols, is impossible. So case 2 was vxy contains two types of symbols, here or here, and there could be a potential case 3 where vxy contains three types of symbols. So in such a case, vxy would start somewhere here among the zeros, would contain all the ones, and would go along the range of 2's. This would be the range of vxy, but you should be able to see that this is impossible due to the third condition of pumping lemma, which says that length of vxy together should be less than or equal to p. But in such a scenario, it should be clear that the length of vxy is greater than p. So that case 3, is not possible, which implies that now we have consumed all possibilities, all possible cases. One case where vxy only contains one type of a symbol, a second case where vxy contains two types of symbols, a third case where vxy contains more than two types of symbols is not possible. We have finished all possible cases, therefore, and in each case we have seen that there exists some I such that uv to the I, xy to the I, z is not in the language. Since this is true in all the cases, we can conclude that due to pumping lemma, by pumping lemma for context-free languages, the given language is not context-free. All this proves that L is not a context-free language.